So let's try to solve one more problem from TIFR 2024, and this is from classical mechanics, and this is a very simple problem. This is all about your spherical pendulum, you can say. So what is given? A particle of mass m is attached to massless string of length L. So this is your length L, this is mass m. The other end is fixed at point P. So at this point it is going to be fixed. So mass m move under gravity and tension of the tension of the string. The motion of a string is described by the generalized coordinate theta and phi. Theta is making angle with the z-axis and phi is the azimuthal angle that will lie in xy plane. So is the azimuthal angle, you can just see. The conjugate momenta for theta and phi is p theta and p phi. So what we have to do? We have to write the Hamiltonian of a system. So what should be the Hamiltonian of a system? Let's try to go for this. So in this problem, this is quite simple, but they have given the potential energy in some different form. So this is one of the interesting thing. So let us try to go for this one. So when we are going to solve particularly this particular problem, so what we have basically this is my z-axis, this is my x-axis, this is my, so this is x, this is y, this one is z, and this is my pendulum. So this angle is theta, and we have this azimuthal angle. So this is your phi. So what is happen? The pendulum can move something like this also, and it can rotate also. So this is the thing. Now here, what will be the Lagrangian? For the Lagrangian of a system, L is equal to kinetic energy minus potential energy, and we can write kinetic energy is very simply half m L square theta dot square plus half m L square sine square theta phi dot square. So this is my kinetic energy. The whole thing is how you will write the potential energy. So you can just think something like that. So if my pendulum is equilibrium, we can assume this point is P, and we can assume this has potential something minus mgl. You can have this potential as 0. You can, some problem, you can take this potential as 0 also. But as if you will see the nature of potential energy, this potential is minus mgl. And if it is going to deviate with this angle, then this potential is minus mgl cos theta. And what will be this difference of this potential energy is minus mgl cos theta minus mgl. So what will happen? This value is minus, this value mgl, and you have 1 minus cos theta. And you can easily write 1 minus cos theta as equal to, that is mgl 2 sine square theta by 2. So you have to also remember this type of thing, that from this particular, you can see that in all 4 options you have this type of potential energy. So this is your potential energy. So this is my potential energy, that is 2 mgl sine square theta by 2. And now we can easily go for the Hamiltonian of a system. So what is my Lagrangian? My Lagrangian is equal to half m L square theta dot square plus half m L square sine square theta phi dot square minus 2 mgl sine square theta by 2. And what is my Hamiltonian? If theta and phi is my generalized coordinate and p theta p phi is my conjugate momentum, then you have theta dot p theta plus phi dot p phi minus Lagrangian of a system. And what you can do, you can just go for theta dot p theta plus phi dot p phi minus half m L square theta dot square minus half m L square sine square theta phi dot square, and this minus minus will plus. You have 2 mgl sine square theta by 2. The whole thing is we have to remove theta dot and phi dot. So how you will go for that? So when you will go for that, del L upon del theta dot is equal to p theta. That value is equal to ml square theta dot. From there, theta dot is equal to p theta upon ml square, and similarly del L upon del phi dot is equal to p phi. That value is ml square sine square theta phi dot and this is your theta dot, and from there phi dot we can have p phi upon m L square sine square theta. So what we will do, we will put theta dot, phi dot, theta dot and phi dot here, and we can get the Hamiltonian. And once we will put it here, then we will easily get your Hamiltonian is p theta square upon ml square, and you have p phi square upon, and that will be 2ml square, 2ml square sine square theta, and plus you have 2 mgl sine square theta by 2, and you will find this will be your answer. In this particular option, I think L square is just left, it is some misprinting, but you will get the option number 1 will be your answer. So you can take p theta something like this, p theta square upon 2 ml square common, and you can have this one is your common, and here you have p theta square plus p phi square, and that will be cosec square theta. So this will be your cosec square theta plus 2 mgl sine square theta by 2. So this is a straightforward, very simple problem, but only difference is that how you are representing your potential energy. So you can represent your potential energy in a different way. Here we have taken my potential energy is mgl 1 minus cos theta, and then this mgl is just a constant, so it will not affect any equation of motion. So you can sometimes take it 0 also. So this is all about dependent on what is your reference. Thank you.